Welcome to this problem-solving session. Today, we'll explore an exciting problem titled Most Beautiful Item for each query. We'll break it down step by step, analyze different approaches, and discuss how to efficiently solve it. Let's dive in. In this problem, you're given a two-dimensional array called items, where each element represents an item with two properties, its price and its beauty. The price is the cost of the item, and the beauty is a measure of its attractiveness. You're also given an array called queries, where each value represents the maximum price you can afford for a specific query. Your task is to find, for each query, the maximum beauty of any item you can afford within that price limit. If no item falls within the price limit for a query, the result for that query should be 0. The output will be an array where each value corresponds to the maximum beauty for the respective query. Essentially, this problem focuses on finding the best item you can buy for a given budget, based on its beauty score. Now let's look at an example to understand the problem better. Suppose the items list is 1, 2, 3, 2, 2, 4, 5, 6, and the queries list is 1, 2, 3, 4, 5. For the first query, with a maximum price of 1, the only item you can afford is 1, 2, so the maximum beauty is 2. For the second query, with a price limit of 2, you can afford 1, 2, and 2, 4, and the maximum beauty is 4. For the third query, with a maximum price of 3, the affordable items are 1, 2, 2, 4, and 3, 2. The highest beauty among these is still 4. Similarly, for a price limit of 4, the set of affordable items remains the same, so the maximum beauty is again 4. For the final query in this example, with a maximum price of 5, you can afford all the items in the list. The most beautiful item is 5, 6, which has a beauty score of 6. Therefore, the output for this example is 2, 4, 4, 4, 6. In another example, consider items equals 10, 100, 20, 200, 30, 300, and queries equals 15, 25, 35. For the first query, you can only afford 10, 100, so the maximum beauty is 100. For the second query, with a price limit of 25, you can afford 10, 100, and 20, 200, and the maximum beauty is 200. For the third query, with a maximum price of 35, all items are affordable, so the maximum beauty is 300. The output for this example is 100, 200, 300. The problem also comes with constraints and edge cases to consider. First, the number of items in queries can go up to 100,000, so the solution must be highly efficient. Each item in the items array contains exactly two values, price_i and beauty_i, both of which can be as large as 1 billion. Similarly, the queries can also have values as high as 1 billion. Some edge cases to handle include scenarios where no items are affordable for a query, in which case the result should be 0. The problem should also work properly when there's only one item or one query. Given the large input size, techniques like sorting and binary search will be essential to solve this problem within a reasonable time frame. To begin solving this problem, one straightforward approach is the brute force method. The idea here is simple. For every query, we iterate through all the items and check which ones are affordable, meaning their price is less than or equal to the query. Among these affordable items, we then find the one with the highest beauty. Although this approach is intuitive and easy to implement, it quickly becomes inefficient as the input size grows. The time complexity is O(m*n), where m is the number of queries and n is the number of items. This means that for each query, we examine every single item, which can be extremely slow when dealing with large datasets. While this method is straightforward, it's impractical for scenarios involving large arrays of items or queries due to its high computational cost. Therefore, we need a more efficient strategy to handle larger inputs effectively. To optimize this process, we can use a strategy that combines pre-processing and binary search. The key insight here is to sort the items by price, which allows us to efficiently group items based on affordability. By sorting the items, we can use binary search to quickly locate the most expensive item within the budget of a given query. Additionally, we pre-process the data to create a maximum beauty so far array. This array keeps track of the highest beauty value encountered up to any given price, so we don't need to repeatedly search for the maximum beauty among affordable items. With this setup, we handle each query by performing a binary search to determine the most expensive affordable item and then directly retrieve the pre-computed maximum beauty. This approach has a complexity of O(n) log n for sorting and O(m) log n for resolving all queries, making it significantly faster than the brute force method for large inputs. The trade-offs here involve some upfront pre-processing cost, but the speed-up during query resolution makes this approach highly efficient. Another alternative is to use advanced data structures like segment trees or Fenwick trees to pre-process the items and efficiently handle range queries. With these structures, we can pre-process the data to answer queries about the maximum beauty within a given price range in logarithmic time. Building the tree requires O(n) log n, and each query takes O log n, leading to an overall complexity similar to the binary search approach. However, the trade-off lies in the complexity of implementation. Segment trees or Fenwick trees require more effort to implement and maintain, and they may not be as intuitive as the binary search method. Given that both approaches offer similar performance, the simplicity and ease of debugging provided by binary search make it a more appealing choice. The focus, therefore, remains on balancing efficiency and implementation simplicity. The key to the chosen approach lies in leveraging the sorted nature of the items. Sorting by price allows us to efficiently group items and use binary search to locate the most expensive affordable item for each query. Pre-computing the maximum beauty so far ensures that once we identify the correct price range, we can instantly retrieve the most beautiful item without additional computation. While sorting introduces an upfront cost of O(n) log n, this is a worthwhile trade-off given the significant reduction in query resolution time to O log n per query. Though alternatives like segment trees can achieve similar time complexity, they add unnecessary complexity to the solution. By contrast, the binary search approach strikes the perfect balance between pre-processing cost, query efficiency, and implementation simplicity. This makes it an ideal solution for handling large datasets effectively while keeping the code clean and manageable. The problem asks us to find the maximum beauty of an item that can be purchased within a given budget for each query. Each item has a price and a beauty value, and if no item fits the budget, we should return 0 for that query. To solve this, we start by pre-processing the items. First, we sort the items by price in ascending order. If two items have the same price, we sort them by beauty in descending order. This sorting ensures that as we iterate through the items, we can maintain the highest beauty seen so far without revisiting previous items. To achieve this, we create a list, max_beauties, that stores the maximum beauty encountered up to each price point. This pre-computation step allows us to efficiently handle queries later. Next, we sort the queries by their budget value while keeping track of their original indices. Sorting the queries in ascending order aligns them with the sorted items list, enabling us to minimize redundant comparisons during the search process. Now, we use the two-pointer technique to match queries with items efficiently. We initialize a pointer, I, to iterate through the sorted items list and a variable, max_beauty, to keep track of the highest beauty encountered so far. For each query, we move the pointer I through the items list as long as the price of the current item is less than or equal to the query's budget. With each step, we update max_beauty to reflect the highest beauty value seen up to that point. Once the pointer has processed all items affordable within the current query's budget, we store the value of max_beauty in the result array at the index corresponding to the query's original position. Finally, after processing all queries, we return the result array. Key insights from this approach include the efficiency gained through sorting and the two-pointer technique. Sorting ensures sequential processing and reduces redundant checks, while the two-pointer technique ensures that each item and query is processed at most once. Additionally, maintaining a running maximum of beauty values avoids recalculating the maximum for overlapping price ranges, saving computation time. We rely on specific data structures to implement this algorithm efficiently. First, we use a list of tuples to represent both the items and the queries. Each item tuple stores a price and a beauty value, while each query tuple contains a budget and its original index. Using tuples allows us to maintain the associations between prices and beauty values, as well as between budgets and their original positions, even after sorting. Next, we use a result array to store the maximum beauty values for each query in the same order as the original input. This ensures that the output matches the order of the query list provided by the user. When analyzing the complexity, we note that sorting the items takes O and log n, where n is the number of items, while sorting the queries takes O m log m, where m is the number of queries. During the query processing phase, each item and query is processed at most once, resulting in an O n plus m time complexity. Combining these steps, the overall time complexity of the algorithm is O n log n plus m log m, dominated by the sorting steps. When implementing this algorithm, it's important to consider edge cases to ensure correctness. For instance, if the items list is empty, all queries should return 0 since no items are available for purchase. Similarly, if the queries list is empty, the result should simply be an empty array. Another case to handle is when all items are too expensive for the given budgets. In such scenarios, the result for those queries should be 0. Additionally, we must handle duplicate prices or queries gracefully. Using stable sorting ensures that the relative order of items or queries with the same key remains consistent. Lastly, for large inputs, the algorithm's efficiency becomes critical. The use of sorting and the two-pointer technique ensures that we can handle large values of n and m efficiently. Let's look at an example to solidify these concepts. Suppose we have items 3, 4, 5, 8, 3, 6, and queries 4, 3, 10. First, we preprocess the items by sorting them by price, resulting in 3, 6, 3, 4, 5, 8. We then compute the maximum beauty values up to each price point, yielding max_beauties equals 6, 6, 8. Next, we process the queries. After sorting the queries by budget while keeping track of their original indices, we get 3, 1, 4, 0, 10, 2. We initialize the result array as 0, 0, 0. For the first query with a budget of 3, we find that the maximum beauty within this budget is 6. For the second query with a budget of 4, the maximum beauty remains 6, as no additional items become affordable. Finally, for the query with a budget of 10, all items are affordable, so the maximum beauty is 8. After processing all queries, we map the results back to the original query order, yielding the final output 6, 6, 8. This example illustrates how the pre-processing, sorting, and two-pointer technique work together to efficiently handle the problem while ensuring correctness for all edge cases. Here, we begin by defining a method called maximum beauty within the solution class. This method takes two inputs, a list of items and a list of queries. First, we sort the items based on their price and, if prices are equal, by their beauty. This ensures that we can process items in an ordered manner. Next, we pre-process the items to maintain a running maximum of the beauty values seen so far. This is done using a variable max_beauty which keeps track of the highest beauty encountered as we iterate through the sorted items. For each item, we update its beauty value to this maximum, ensuring that every item reflects the best possible beauty for its price range. After that, we prepare the queries by pairing each query value with its original index and sorting these pairs. This allows us to map results back to the original query order later. Now, we initialize a result list with zeros, which will store the maximum beauty for each query, and set a pointer j to track the current position in the items list. For each query, we adjust the pointer to include all items that are affordable based on the query's price. If we encounter any affordable items, we update the result for that query to the beauty value of the most expensive affordable item, which is the maximum beauty at that price point. Finally, after processing all queries, we return the result list. This list contains the maximum beauty values corresponding to each query, arranged in the same order as the input queries. By leveraging sorting and preprocessing, this implementation efficiently computes the desired results while ensuring that we only iterate through the items and queries in a structured way. This completes the solution for the problem. Here, we start by importing the necessary libraries and defining our class and method. The goal of this implementation is to determine the maximum beauty of items that can be afforded for each query. The first step is to sort the items array based on their prices. In case two items have the same price, sorting ensures that their ordering remains stable. Next, we pre-process the items array to maintain a running maximum of beauty values. This means that as we iterate through the items, every item's beauty value is updated to reflect the maximum beauty seen up to that point. This ensures that once the array is processed, any item will have the correct maximum beauty associated with its price or lower. After this, we prepare to handle the queries. To do so, we create an auxiliary array that stores each query paired with its original index. This allows us to sort the queries by their price while still being able to map the results back to the original order of the queries. Sorting the queries with index array ensures that we can process the queries efficiently in increasing order of price. Finally, we initialize a result array to store the maximum beauty for each query and a pointer j to iterate through the sorted items array. The logic for computing the results will follow in the next part of the method. Now, we process each query in the queries with index array. For each query, we extract the price and its original index. The pointer j is used to iterate through the items array. As long as the item's price is less than or equal to the current query price, the pointer advances, ensuring that we consider all items that are affordable for the given query. Once the loop exits, we check if any items were affordable. If the pointer has moved at least once, this means there are items whose prices are less than or equal to the query price. In this case, the item's beauty value at the position j1 represents the maximum beauty among all affordable items for the query. We store this value in the result array at the position corresponding to the query's original index. If no items are affordable, the result for this query is simply 0. After processing all the queries, the method returns the result array, which contains the maximum beauty values for all queries in their original order. In this example, we're given 3 items with their respective prices and beauty values, along with 3 queries representing the maximum price a customer is willing to pay. The first step is to sort the items by price. In this case, the items are already sorted as 10, 100, 20, 200, 30, 300. Next, we pre-process the items to ensure that each entry reflects the maximum beauty available at or below its price. Starting with a max_beauty of 0, we iterate through the items. For 10, 100, the maximum beauty becomes 100. For 20, 200, it updates to 200. Finally, for 30, 300, it becomes 300. After this pre-processing, the items remain the same but are now ready for efficient query processing. Now, we move on to sorting the queries along with their indices to maintain their original order later. The queries 15, 25, 35 are paired with their indices to form 15, 0, 25, 1, 35, 2, which are already sorted by price. To compute the results, we initialize an array result equals 0, 0, 0, and a pointer j equals 0 to traverse the items. For the first query, price 15, we include items with prices up to 15. The pointer moves to j equals 1, and the highest beauty seen so far is 100. We update result 0 equals 100. For the second query, price 25, we include items with prices up to 25. The pointer moves to j equals 2, and the highest beauty is 200. We update result 1 equals 200. For the third query, price 35, we include items with prices up to 35. The pointer moves to j equals 3, and the highest beauty is 300. We update result 2 equals 300. The final result for this example is 100, 200, 300. In the next example, some queries cannot afford any items. The items are 5, 50, 10, 150, 20, 250, and the queries are 1, 10, 15. First, the items are already sorted by price, so no reordering is needed. Next, we pre-process the items to ensure that each entry reflects the maximum beauty available at or below its price. The items remain unchanged as 5, 50, 10, 150, 20, 250. The queries are sorted with their indices 1, 0, 10, 1, 15, 2. To compute the results, we initialize result equals 0, 0, 0, and start with j equals 0. For query 1, no items are affordable, so result 0 equals 0. For query 10, items up to price 10 are included, and the maximum beauty is 150. We update result 1 equals 150. For query 15, items up to price 15 are included, and the maximum beauty remains 150. We update result 2 equals 150. The final result is 0, 150, 150. Finally, in the edge case where all queries are higher than the maximum price of the items, such as queries 3, 4, 5, each query simply includes all items, resulting in beauties of 30, 30, 30 for all queries. To analyze the time complexity of our solution, we start with the sorting of the items list. Since we sort the list based on both price and beauty, this operation involves comparing elements. With n being the total number of items, sorting requires n*log n time. Next, we pre-process the maximum beauty values by iterating through the sorted items list. This involves a single linear pass, making this step n. Additionally, the queries are paired with their indices and sorted, which is another sorting operation. With m as the number of queries, this step takes m*log m time. These are the initial building blocks of our time complexity analysis. For the next step, we process each query. Here, a pointer j is used to traverse the items list and identify the items that are affordable for the current query. The pointer only moves forward and traverses the items list exactly once across all queries, contributing n overall. Since we also loop through the queries list, this adds m. Combining these, query processing takes m plus n. Now, summing up all the steps, we have the sorting of items at n*log n, pre-processing beauty at n, sorting queries with index at m*log m, and query processing at m plus n. The total time complexity is therefore dominated by the sorting steps, resulting in n*log n plus m*log m. When it comes to space complexity, we start with the input storage. The items list of size n and the queries list of size m both contribute to the space usage. For auxiliary storage, the queries with index list stores tuples containing the queries and their indices, requiring m space. The result list, which holds the final answers, also requires m space. Since sorting operations are typically in place, no extra memory is needed for sorting. Furthermore, the pre-processing step modifies the items list in place, storing the maximum beauty values without additional space. Therefore, the overall space complexity is n plus m, dominated by the size of the input. Comparing this optimized solution to a brute force approach highlights its efficiency. In a naive method, for each query, we would iterate through all items to find the maximum beauty of affordable items, leading to a time complexity of m*n. This becomes computationally expensive when both n and m are large. The optimized solution, on the other hand, reduces the time complexity to n*log n plus m*log m by utilizing sorting and preprocessing. The preprocessing ensures that the maximum beauty for a query can be obtained in constant time 1, leveraging pre-computed data. Importantly, the time complexity remains consistent n*log n plus m*log m across best, average, and worst cases, as the sorting and linear operations are deterministic, regardless of input values. To understand why the time complexity is n*log n plus m*log m, we focus on the dominant operations. Sorting the items and queries with index lists are the most computationally expensive steps, each contributing n*log n and m*log m, respectively. The pre-processing and query handling steps add linear terms n and m, but these are asymptotically smaller and do not affect the overall big O complexity. This mathematical breakdown demonstrates that the optimized solution is efficient and well-suited to handle the problem within the given constraints, offering a significant improvement over the naive m*n approach. When solving this problem, there are several common mistakes to watch out for. First, an inefficient brute force implementation is a frequent pitfall. This involves iterating through all items for each query, leading to a time complexity of n*m, which becomes infeasible for large inputs. This approach simply does not scale and will often result in time limit exceeded errors. Another significant issue is neglecting to sort the items or queries at the start. Without sorting, you end up with redundant comparisons and unnecessary complexity, whereas sorting can pave the way for more efficient techniques such as binary search or two-pointer strategies. Finally, incorrect handling of edge cases is often overlooked, such as dealing with empty arrays for items or queries that don't match any items, or items with duplicate prices. Overlooking these cases can lead to incorrect outputs or runtime errors, making it critical to address them explicitly in your solution. Another factor to consider is unnecessary space usage. This can happen when you store intermediate results or duplicate arrays without a clear reason, which increases memory consumption and may cause memory limit errors, especially in constrained environments. Additionally, after sorting, some developers still use linear search instead of taking advantage of binary search. Linear search may seem simpler, but it's suboptimal when working with sorted data, as it fails to utilize the logarithmic time complexity benefits of binary search. By focusing on space-efficient strategies and leveraging binary search for lookups, you can avoid these common inefficiencies and improve the overall performance of your solution. In interviews, optimization is often the primary focus, so it's important to go beyond brute force solutions. Be ready to explain your thought process for reducing time complexity, such as utilizing sorting or binary search. Interviewers also value the ability to communicate trade-offs, like explaining why sorting upfront might be a better choice compared to iterating multiple times. Handling edge cases explicitly is another key aspect. It's helpful to clarify how you plan to deal with scenarios like empty inputs or edge queries before you start coding. Lastly, recognizing underlying patterns in the problem can give you an edge. For example, this type of problem often involves sorting, searching, or using prefix sums. Being able to quickly identify these patterns will help you craft an efficient solution more effectively. This problem shares similarities with several other LeetCode challenges, making them great practice opportunities. For example, LeetCode 300, Longest Increasing Subsequence, features the use of binary search and dynamic programming concepts, which are also relevant here. LeetCode 238, Product of Array Except Self, involves optimization through prefix computations, a technique that can be adapted to this problem. LeetCode 658, Find K Closest Elements, relies heavily on sorting and binary search strategies, which align closely with the concepts we've discussed. Lastly, LeetCode 1235, Maximum Profit in Job Scheduling, integrates sorting and binary search to achieve efficient solutions. Reviewing these problems can help reinforce the patterns and techniques needed for this challenge. There are also alternative approaches and trade-offs to explore when tackling this problem. The two-pointer technique is one option, where you sort both items and queries and then iterate through them simultaneously using two pointers. This method minimizes redundant comparisons and achieves a time complexity of O n plus m after sorting, but it requires careful implementation to ensure the pointers remain synchronized. Binary search is another effective approach. After sorting the items, you can use binary search, such as Python's bisect module, to efficiently find the maximum price satisfying each query. While this reduces the lookup time to O log n per query, it does introduce some initial overhead due to the sorting step, which is O n log n. Finally, you might consider using prefix sums or pre-processing tables to store cumulative results, such as the maximum price up to each index. This allows for quick query resolutions in O1 or O log n time, but it requires additional space and pre-processing time. Each of these methods has its strengths and trade-offs, so selecting the right one depends on the specific constraints and requirements of your task. Great job! We've successfully solved the problem and explored key concepts like sorting and binary search. Remember, pre-processing and optimization are powerful tools in problem solving. Thank you for watching, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!